Okay, lesson 14 in our chapter 6, unit 6, about graphs of trig functions. This one here is going to talk about graphs of periodic functions. Page 363, 13 to 29, 37 to 39, 45 to 50, 53, 54, all those. So really, what we want to talk about today is what is a periodic function and what is its period. Well, let's take a look real quick here. A function is periodic if and only if the y values repeat on a consistent basis. And that consistent basis is called a period. How often are these y values repeating? And they can't just repeat once. Take a parabola, for instance. A parabola. Do the y values repeat? Yes, but this is not a periodic function. And the reason I say that is, well, this y value and this y value repeat on that set of x's. But this y value and this y value repeat, but that's on a different set of x's. When the y values repeat, they have to repeat by the same amount of x's, or the same amount of time. Take a pendulum. If you take a pendulum, you slide it off to the side and you let go, it swings away and it swings back to where your hand was, and then it swings away and it swings back to where your hand was. That's a periodic idea right there. Every time that gets back to your hand, it's the same amount of time as it was the time before. And if you look at it from in front, you can see that the y values repeat all the way across and all the way back, and then all the way across and all the way. We get repeating y values on consistent time frames. So, a function is periodic if, for some real number alpha, f of x plus alpha is equal to f of x for all x in the domain of f. So for every number that you can plug in, if you can get the exact same y value by just adding a certain value to everything, you've got a periodic function. The least positive value of alpha for which f of x equals f of x plus alpha is the period. That alpha represents the period on which this is going to happen. That came directly off of page 359 if you want to get a better copy of it. So let's just see if we can determine if something is periodic. Here I've got a couple of graphs. I got more down here. They're just too big to do it all in one time. Okay, so determine if the function is periodic. If it is, state its period. So when we're looking at A here, notice this y value is the same as that y value is the same as that y value. This y value is the same as that y value is the same as that y value. Now, I picked those, for instance, because they're not repeating on an up and a down cycle. But notice, if I drew in this little thing right here, my little gauger device, and I start to slide it saying, hey, it's going to go along that, notice the y values all the way along match in that up cycle. If I move over to the next one, notice I didn't change the size of my little device. It's still showing that the y values are staying exactly the same at exactly the same distance apart. Now let's take it along the blues. If I take these two blues and I slide down this line, notice those are staying exactly the same all the way along. This is repeating. These values here on this upswing repeat right here again on this upswing. Repeat again on this upswing. These downswing values here repeated here. But all of these repeat along all of these. This first part repeats here. Now notice there's an arrow there saying it probably continues. So what we're seeing here is that, yes, we have repeating y values on a specific amount of time. They're repeating very, very often. Well, the question is, how much is this gap right here? Well, if I put that there, it says it's 4. The period is 4. When I'm at 1, ooh, everything just kind of went goofy. And when I'm at 1, we're at 5. At 5, we're at 9. At 4, we're at 8. Very, very periodic. Yes, that's a periodic function. And this little mark here that I got is really representing the length or the distance of our period. That happens to be our period. Now, let's look at B. B, again, has repeating y values. All these y values repeat. 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 Definitely a pattern going on. However, if I was going to be asked, is this a periodic function? My answer is no. Although there's a pattern, the y's are not repeating on a pattern. The y's are the same for a while, and then they change to something new, and are the same for a while. Up above in A, I'm pretty confident saying if I needed to know what the value at 10 is, I just have to look at what the value of 6 is. If I want to know what the value at 12 is, I just need to look at the value of 8. If I want to know what the value of 13 is, I just need to look at what the value of 9 is. The y values are repeating. F of x plus alpha is equal to f of x. Up here, f of x plus 4 is equal to f of x. The y values are the same. On B, it's not the case. From 0 or -1 to 2, we're all one y value. But from 2 to 5, we're a different y value. I'd have to add a number outside the function, not inside the function. B is not periodic. Periodic are like A. You can see it is a repeating pattern. The y's change for a pattern, and then they repeat again for a pattern. It just keeps going that way. Let's take a look at C. C, nice and very curvy. Do we have repeating y values? I'm going to go with yes. I'm going to make my little bar again. So if I say, I'm going to pick up right here, and I notice the next time it repeats exactly like that is right there. Notice in both cases, as we're moving left to right, we're on a downhill slide. Now, if I slide along here, notice we're always in the same spots. And what if I jump a gun? And I go and I slide along there. They're right on it. Now what if I go along these other loops? Yeah. This is kind of like the epitome of a periodic function. Yes, this is periodic. And it's period. How often does it repeat? Well, at negative pi and at positive pi, we had the same value. Then again, at 3 pi, we had the same value, where they were all on a downward slope at 0. That distance is 2 pi units apart. Now, what if I slide it over, take away my down arrows, and say, let's look at it from an up point of view, from right here to here. The 0 and the 2 pi are both in the same spot on an up slide. So we would say the period is 2 pi. Now, just to be honest with you, this is the graph of y equals sine x, where x would be our angle, so to speak, in a radian measure. Sine of 0 is 0. Sine of pi is 0. Think about that from the unit circle. Now, there are some properties of this graph that we need to be made aware of. First one, the period is 2 pi. We figured that out already. Second one, The domain is a set of all real numbers. We can plug in any number in that for our x, and it's going to give us a value out. All real numbers. The range is a set of real numbers between -1 and 1. If you look at that graph, notice its lowest spot is at -1. Its highest spot is at +1. And we only oscillate between -1 and +1. The x-intercept are located at every pi n, where n's an integer. Yeah. Notice every x-intercept. -1 pi, 0 pi, 1 pi, 2 pi, 3 pi. The x-intercepts of a sine graph are at a whole pi value. The y-intercept is at 0. Yep, we got the point 0, 0. The maximum values are y equal 1, occur when x is pi over 2. That's this one right here. This is pi over 2. We call that our first spot. And every 2 pi n from there, where n's an integer. Well, 2 pi is the period. That's why there's a 2 pi sitting right here. The period times some integer value, we're going to get back to the exact same spot we had. 2 pi from here is sitting right up there. Or if we go back the other direction, it's sitting right over there. Now, the minimum is at -1, and occurs whenever x is 3 pi over 2 plus 2 pi n. Where does that take place at? Well, that's right here. This is 3 pi over 2. Halfway between 1 pi and 2 pi is 3 pi over 2. Again, the 2 pi is just saying one full circle, loop around the unit circle. And is a whole number of times of doing that, either positive or negative directions. So those are all properties of a sine x graph. It is a periodic function. It repeats every 2 pi. Okay, let's take a look at a different graph. Let's take a look at this one. Okay, we can tell by looking, hopefully, and answer the question, is it periodic? Yes. What's its period? How often is this cycle repeating? Well, let's see. It's at 1 at 0, and it's at 1 again at 2 pi. Those are both at the top of the lists. It's at -1's at negative pi and positive pi. Well, that's 2 pi apart. And then again at 3 pi. Period, once again, is 2 pi. Is this a sine graph? Because it's got a period of 2 pi. It's a set of all real numbers. The range is between -1 and +1. Uh-oh. See that line number 4 is up there? The x are located at n's. It didn't cross 0 at a pi. It crossed at a pi over 2. And 3 pi over 2. And 5 pi over 2. It's not hitting the x-axis at a pi. This is not a sine function. This is a cosine function. Notice it looks very similar to a sine function, but slightly different. Now, if you think back when we did that project before Christmas, yeah, this was one of the graphs we got. Well, what are its properties? Well, the first 3 are identical, and that's kind of what I was talking through there when I thought maybe it was a sine. Period's 2 pi, domain's all real numbers, between -1 and 1. But then it fell apart when we looked at the zeros. The x-intercepts are located at pi over 2 plus pi n, where n's an integer. So every 1 pi, we're back at a 0. The x-intercept, the y-intercept is at a +1 for a cosine. Well, think about that. What is the cosine of 0? Use your unit circle sheet if you have to. Cosine of 0 is 1. The maximum values of 1 occur at every pi n, where n is an even integer. And it occurs at -1 when x is pi n. But this time, whenever n is an odd integer, we're at the bottom. So, on this first page, we had a cosine graph, which is periodic, and here's all the information we found about it. We had a sine graph, which is periodic, and here's everything we found out about it. We had a function that was not periodic. It's not repeating over and over and over again in the same set of y's on a pattern. And here we had a nice little zigzag type thing, almost like a sine and cosine graphs, but these are like straight lines. So let's try some more. Let's call this one E, this one F, and this one G. So I'd like you to take a second, take a look, determine if you think E is a periodic function. Yes or no? If yes, what's its period? If no, why not? Take a look at F. Do you think F is periodic? Yes. Then tell me what you think the period is. No. Then why not? Take a look at F. Do you think it's periodic? Yes. What's its period? No. Why not? G, F, E. Okay, I'm going to start with G. To me, G is easy. Is it periodic? Answer is no. Although the y's repeat, they're not repeating on the same set of x values. The y's at the top have different x's than the y's halfway down as compared to those right near the x-axis. The other thing, it doesn't keep repeating. It's just one set of y's that matches another set of y's, but it's not periodic. F. I would say F is periodic. The y's seem to be getting the exact same values. They're all going up to the same height. They all, okay, badly drawn graph. Excuse me. But the period seems to be 1 unit. They're all at the empty circle right on a whole number. They seem to be at the top near a top of a whole number. They're going to add the same slants all the way along. I would say F is periodic with a period of 1. E. Wow. Because it was hand-drawn and not machine-drawn, makes it tough to determine. It does have some arrows there. Could this be like an upside-down x to the 4th graph, in which case, no, it's not periodic. But is this just something that keeps repeating like this and we haven't figured out what it is yet? Well, what we can do is we can check some numbers. Okay, we're here at 0 at -3, and it kind of looks like we're going in an upwards direction. Next time we're over here going in that same upward direction. That's a grouping of 5 apart. That's 5 apart. Now, let's look at the downslope. Right here we have a downslope where we're at 0 and we're going down. Here's another downslope and we're going down. Ooh, that looks like it might be out at 4, which says this has a length of 5. Okay, what about our tops? Where are we at the tops? The top seems to be somewhere around -2 and around +3. That seems to have a distance of 5. So based on those, I would lean towards yes, it's periodic, just drawn badly by the guy who wrote on the board, and the period is 5. But if you were one to say, no, I could go with that real easily, because it doesn't seem to be flowing real well. But I would lean towards E as being yes. Period of 5. F probably on this page is the best, easiest one to say yes to, because it does have repeating values. Again, hand-drawn, it's hard to tell. Okay, so what do we got? Lesson 14, page 363, 13 to 29. 13 to 18 are just saying, is it a periodic function? Is this thing that's a repeating pattern all the way down the line? Yes or no? And then what's its period? 19 to 24 are finding trig values. Great chance to use the unit circle to help you find them. Remember, on that unit circle, those sines and cosines just repeat each other. Or you can look back at the graphs I had on the notes, or you can get your own graph on your calculator, make sure you're in radian mode, or in your book, there's a graph of it. 37 to 39, they want to know, is the graph a sine graph or a cosine graph? And what I suggest you do is you compare the graph in the book with y equals sine x or y equals cosine x. The 45 to 50, you're trying to figure out where is like sine of x is less than or equal to cosine of x. Here's a great chance to use Desmos or your graphing calculator, as long as you can distinguish between them. Let the one side be one y, and let the other side be another y. Graph the two, and when are the sines less than the cosines? From what x value to what x value? So your answer is going to have probably inequalities in there with numbers. So from where to where? Unless it's only at one spot. But since these are repeated patterns, it will go on them. Now, if you're going to do it on Desmos, I recommend that you set the domain from negative pi over 4 to 9 pi over 4. And I would do a step of pi over 12. I don't know why I got a 0 and a 2 pi on there. I guess that's just so you can clearly, easily tell where the 0 to 2 pi part is. There's your assignment. You've got this.